Tonight, the sun set the way it always does, a soft, familiar warmth sinking beneath the horizon, the same steady yellow star that has watched over every evening we have ever known. But that quiet, reliable star is not eternal. Tonight, we're going to drift through the final days of our home star. No one expects a violent explosion, for the sun is too small to ever go supernova. The sun's fate is a slow expansion, not a sudden blast. While the popular imagination often pictures a star ending in a blinding flash of gamma rays and a shock wave that tears through the quadrant, the reality for a G-type main sequence star is far more patient. It is a gradual swelling, a steady inflation of plasma that transforms a yellow sphere into a bloated red giant. Picture the silence of the void as we move away from the familiar blue of Earth. We are drifting past the orbit of Mars, feeling the cold vacuum press against us. While ahead, the sun begins to change. The light is no longer the crisp white yellow of a summer afternoon. It is deepening. It is shifting toward a heavy bruised orange. The surface of the star is no longer a tight humming ball of fusion, but a shimmering translucent veil of gas that seems to breathe. The scale of this transition is measured not in days but in epochs. We are witnessing a process that takes millions of years to unfold, where the internal pressure of the stellar core begins to fight a losing battle against gravity. For billions of years, the sun has existed in a state of hydrostatic equilibrium, a perfect balance between the inward pull of its own mass and the outward push of nuclear fusion. But as the hydrogen in the core is exhausted, that balance breaks. The core contracts, heating up to temperatures that defy human comprehension, while the outer envelope of the star begins to push outward, expanding like a slow-motion bubble. It is a transition from a stable engine to a fragile, shimmering giant. We are watching the very definition of our solar system dissolve. The distances that once felt infinite, the millions of miles between planets, now feel like a narrowing corridor. The sun is growing, claiming more of the dark, filling the horizon with a glow that is cooler in temperature but overwhelming in its sheer size. There's a strange peace in this inevitable growth. There are no sirens, no sudden alarms. There is only the steady, rhythmic increase of luminosity, a whisper of heat that reaches out to the planets, slowly warming the frozen wastes of the outer rim. The solar wind, once a stream of particles, becomes a torrent, stripping away the atmospheres of worlds that have known only cold for eons. We are floating in a sea of orange light, watching the architecture of the heavens rewrite itself. The sun does not fight its end. It simply expands, drifting into a state of being that is alien to everything we have ever known. The yellow dwarf that gave life to the first cells in a primordial ocean is becoming something else. A red giant, a celestial ghost of its former self, stretching its limbs across the void until the space between the star and its children vanishes. But the path to this end was long misunderstood. For decades, we imagined a simple, linear aging process. The consensus of stellar evolution was drawn in straight lines and predictable slopes. Early stellar models from the mid-20th century suggested a graceful, steady decline. The prevailing theory of the time, rooted in the foundational principles of hydrostatic equilibrium, painted a picture of a star that would simply run out of fuel and fade. In these early calculations, the sun was expected to drift toward a quiet cooling phase, shrinking slowly as its internal fire dimmed, like a campfire burning down to a heap of gray ash. The mathematics of the era suggested a symmetry to the end, a mirror image of the star's birth, where the energy output would drop in a worked a consistent, measurable cadence until the light finally vanished. This was the comfort of the old map. It presented the death of a star as a subtraction, a gradual loss of heat and volume. Astronomers believed that the transition from a main sequence yellow dwarf to a stellar remnant would be a linear descent. There was a belief that the star would remain relatively compact, its radius staying within a manageable boundary while its temperature dipped. Now, the universe in this version of the story was a place of orderly shutdowns. The sun would simply grow tired, its luminosity sliding down a gentle curve, allowing the planets to freeze in a slow, rhythmic sleep. It was a vision of a cosmic autumn, where the leaves fell one by one in a predictable sequence of decay. The models relied on the idea that gravity and pressure would maintain a tight grip on the stellar material, even as the hydrogen vanished. The expectation was that the core would contract, and the star would follow suit, collapsing inward with a quiet dignity. There was no room in these early equations for the violent expansion we now know to be inevitable. The science of the time viewed the star as a closed system of stability, where the end was merely the absence of the beginning. We looked at the sky and saw the sun as a permanent fixture that would only ever diminish, never grow, never threaten the boundaries of its own solar system. This linear perspective ignored the hidden volatility of the helium ash accumulating in the center. The old belief that stars simply fade away linearly failed to account for the desperate struggle of a dying core. It assumed that once the hydrogen was gone, the story was over. It did not anticipate the secondary ignition, the sudden realization of a new fuel source that would push the star's outer layers into the void. The early theorists saw a candle flickering out, when in reality they were looking at a fuse that had not yet reached the powder. The symmetry they sought was an illusion, a byproduct of incomplete data and the limitations of the 20th century astrophysics. We believed the sun would go quietly into the night, retreating into itself. We imagined a future where the Earth would simply grow colder and colder, a slow freeze under a shrinking, dimming light. The old models promised a predictable exit, a slow fade into the background radiation of the universe. The mathematical elegance of the linear decay provided a sense of security, a feeling that the end was a distant, receding shore. But the cosmos rarely follows the path of least resistance, and the stability of the early models was a mask for a much more chaotic transformation. The numbers did not line up with the reality of the stars we were beginning to observe in the deeper reaches of the galaxy. The linear fade was a theory of convenience, a simplification that worked on paper but failed in the face of the actual mechanics of nuclear fusion. The assumption that the sun would shrink as it cooled was the primary error, a misunderstanding of how a star handles the death of its core. The pressure building inside the sun was not seeking a quiet exit, it was seeking a way out. The tension between the collapsing core and the expanding envelope was not a steady decline, but a mounting pressure cooker of stellar gas. The truth, however, was far more volatile. Expectation, a slow linear fade into a cold dark. Reality, a swelling giant that refuses to vanish. The true nature of the sun's final act was brought into focus in a 1993 paper published in the Astrophysical journal by Sackmann, Boothroyd, and Kraemer. Their research dismantled the idea of a quiet retreat, revealing instead a violent internal reorganization that would force the star to expand far beyond its current boundaries. They showed that the sun is not merely running out of fuel, but is instead preparing for a desperate transition of power. As the hydrogen in the core is exhausted, the gravitational pressure becomes an unbearable weight, crushing the remaining helium into a dense, superheated sphere. For a long time, the star exists in a state of precarious imbalance. The core collapses further and further, becoming a concentrated knot of energy, while the outer envelope of the star begins to bloat. This is the beginning of the red giant phase, a period where the sun will swell until it consumes the very space where our inner planets once drifted. The mechanism driving this growth is a phenomenon known as the helium flash. When the core reaches a critical temperature and density, the helium does not ignite slowly. Instead, it detonates in a sudden runaway nuclear reaction. In a matter of minutes, a surge of energy is released that is so intense it creates a shock wave through the stellar interior. This flash does not destroy the star, but it provides the necessary pressure to push the outer layers of the sun outward, expanding the stellar envelope by hundreds of times its original size. This is not a gentle growth. It is a systemic failure of the star's previous equilibrium. The photosphere, the visible surface of the sun, will drift outward, cooling as it expands, shifting its color from a brilliant white-yellow to a deep, haunting crimson. The sun will no longer be a distant point of light in the sky, but a wall of glowing plasma that dominates the horizon. In this new state, the sun becomes a predator of its own system. The expansion is so vast that the orbits of Mercury and Venus are no longer safe harbors. They will be overtaken by the outer atmosphere of the star, their rocky surfaces vaporizing as they are swallowed by the solar envelope. The sun will not simply be larger, it will be an ocean of fire that erases the boundaries between the star and its closest children. The 1993 findings by Sackmann and his team clarified that this expansion is an inevitable byproduct of the star's mass. Because the sun is a low-mass star, it cannot simply collapse into a black hole or explode as a supernova. It is forced into this slower, more agonizing transformation, where it must grow larger to survive its own internal collapse. The helium flash is the catalyst, the moment the star decides to trade its stability for size. We are witnessing a reversal of the solar order. For billions of years, the sun has been the anchor, a stable center around which everything revolved. Now that anchor is becoming the void. The space that once held the void is now filled by the star. The distance that once protected the planets is now a bridge that the sun is crossing. The sheer volume of the expanded envelope creates a new kind of luminosity. While the surface is cooler than the current sun, the total surface area is so immense that the star actually becomes brighter, casting a dim red light across the outer reaches of the solar system. The darkness of space is pushed back not by a focused beam, but by a swelling tide of plasma. This expansion is the physical manifestation of the star's struggle against gravity. The core wants to collapse, but the shell wants to fly away. The result is a bloated, shimmering sphere that stretches the limits of the solar system's geometry. The inner planets are not just destroyed, they are absorbed, their atoms becoming part of the sun's own outer atmosphere. The numbers provided by the Astrophysical journal describe a transformation of scale that defies human intuition. The sun will grow until its edge reaches the orbit of Earth, and perhaps beyond. The sky will no longer have a sun. The sky will be the sun. There will be no more constellations, no more distant stars visible in the night, only the endless, undulating surface of a red giant. This is the reality of the stellar life cycle. The sun is not fading, it is overflowing. It is a process of shedding the old self to make room for a new, more unstable form. The helium flash is the trigger, and the red giant is the result, a temporary monument to the star's refusal to simply vanish. To understand this growth, we must move closer. We move closer now, drifting toward the outer skin of this expanding entity. The image of the sun as a sharp, defined yellow disk, the one that has illuminated every human memory, is gone. In its place is a horizon that no longer curves away from us, but rises to meet us. As we descend toward the photosphere of the red giant, the star ceases to look like a solid object and begins to look like a translucent, bubbling ocean of orange plasma. The sensory texture of this new surface is a paradox of physics. In our current era, the sun's surface is a searing white-yellow, a place of violent intensity. But as a red giant, the photosphere has cooled. It is no longer a blinding white heat, but a deep brooding amber, a color that suggests a dying ember on a cosmic scale. Yet, because the star has swelled to such an impossible size, the total amount of light it emits is vastly higher than it ever was during its youth. It is cooler in temperature, but more luminous in presence. We are now floating within the upper reaches of this atmosphere where the plasma does not behave like a liquid, but like a shimmering gelatinous haze. Great convection cells, larger than entire continents, rise and fall in slow motion. These are not the small granules we see on the modern sun. These are colossal plumes of gas, undulating like slow-motion waves in a sea of liquid gold. The light here is thick, heavy, and pervasive. It does not come from a single point in the sky, but surrounds us from every angle, filling the entire horizon of what remains of the Earth. The sky has vanished. There is no blue, no black, no void. There is only the photosphere. The Earth, now a scorched cinder, is no longer orbiting a star. It is swimming through the outer layers of one. We can see the plasma brushing against the atmosphere of the planet, a soft glowing tide of ionized gas that flows around the globe like a solar wind made manifest. The light is a constant suffocating orange, a hue that persists even when the planet turns away from the core, because the sun now wraps around the Earth, cradling it in a sphere of incandescent gas. The air is no longer air. The heat has stripped away the nitrogen and oxygen, leaving only a thin, shimmering veil of minerals and metals that glow in the red light. We are witnessing the final intimacy between a planet and its parent. The boundary between the two has dissolved. The photosphere is not a wall, but a transition, gradient of heat and light that stretches for millions of miles. The silence of this place is absolute, yet the visual noise is overwhelming. We see the plasma swirling in great slow vortices, creating patterns of light and shadow that look like marbled stone on a planetary scale. The luminosity is so pervasive that it penetrates every crevice of the dead world, illuminating the deepest canyons and the highest peaks in a monochromatic amber glow. The light does not cast shadows. It saturates everything, erasing the contrast between day and night. This is the state of the solar system in its twilight. The precision of the old orbits has been replaced by the chaos of fluid dynamics. The Earth is no longer a traveler in the void, but a passenger in a river of fire. The scale of the photosphere is so immense that the concept of a distance to the sun becomes meaningless. You are not looking at the sun, you are inside the sun. The very fabric of the environment has shifted from the vacuum of space to the dense, glowing medium of a stellar envelope. The light we see now is the result of the shell-burning hydrogen. In a frantic attempt to hold back the crushing weight of the core, it is a fragile luminosity, a shimmering facade of gold and orange that masks the instability beneath. We can see the surface pulsing, expanding, and contracting in a slow, rhythmic breath, as if the star is trying to shake off its own mass. Each pulse sends ripples through the plasma, waves of heat that wash over the remnants of the inner planets, erasing the last traces of their geological history. The photosphere is a place of haunting beauty, a glowing ocean that spans the reach of our old world. It is a reminder that the stability we relied upon for 4 billion years was merely a brief pause in a much larger, more volatile cycle. The gold of the red giant is the color of an ending, a final brilliant flare before the inevitable collapse. The scale of this transformation is nearly impossible to grasp. To grasp the sheer magnitude of this change, we must leave the sensory experience of the plasma and look at the geometry of the system from a distance. Imagine the sun as it is today, a single grain of sand resting on a vast, dark floor. In this scale, the planets are tiny specks of dust orbiting at measured distances, separated by an emptiness that feels absolute. Now, watch as that grain of sand begins to swell. It does not merely grow, it erupts in a, slow-motion bloom of light, expanding until that single grain has become the size of a beach ball. In this transformation, the space where Mercury once held its orbit is gone, swallowed instantly. Venus, which once danced in the warmth of the inner system, is consumed next. The beach ball of fire now occupies the very territory that defined the inner solar system for billions of years. This is the physical reality of the stellar radius expansion. The sun's radius will increase by a factor of approximately 200. To put this into a concrete ratio, the distance from the center of the sun to the surface of the Earth is roughly 150 million kilometers. In its red giant phase, the sun's outer envelope will push outward, claiming a significant fraction of the distance. While the core remains a dense, shrinking knot of helium, the photosphere becomes a sprawling ghost of its former self, stretching across the void to erase the boundaries we once knew. The ratio of the sun's growth relative to the Earth-Sun distance is the true measure of our fragility. We are not dealing with a simple increase in heat, but a physical encroachment of the star's body into the living space of its children. If you were to stand on a distant moon of Jupiter, looking back toward the center of the system, the sun would no longer look like a disk. It would appear as a wall of light, a curved horizon of glowing gas that dominates the entire sky. The emptiness of the inner solar system, once a vacuum of silence, is now filled with the heavy, humming presence of the stellar atmosphere. The planets are no longer orbiting a distant point of light. They are swimming through the outer fringes of the star itself. This is a process of reclamation. The sun is taking back the space it once allowed the planets to inhabit. The physics of this expansion is driven by the desperation of the stellar core. As the hydrogen in the center is exhausted, the core contracts under its own gravity, heating up to temperatures that allow a shell of hydrogen just outside the core to begin fusing. This shell burning creates an outward pressure so immense that it overcomes the gravity of the outer layers, pushing the photosphere outward. In a massive luminous bubble, the star becomes a paradox. Its core, is becoming smaller and denser, while its body becomes larger and more diffuse. It is a star that is collapsing inward and exploding outward at the same time. The result is a luminosity that is hundreds, perhaps thousands of times greater than what we experience today. The light is no longer a focused beam, but a pervasive, omnidirectional glow. The ratio of the sun's radius to the Earth's orbit means that the Earth is no longer merely receiving light. It is being bathed in the actual substance of the star. The atmosphere of our world is stripped away, not by a wind, but by the physical arrival of the solar envelope. The ground becomes a liquid, and the liquid becomes a gas, all while the horizon is filled with the undulating golden skin of the red giant. We see the solar system as a clockwork mechanism of orbits and distances, but the red giant phase reveals that these orbits are merely suggestions. The gravity of the expanding star changes, the solar wind intensifies, and the very map of the neighborhood is rewritten. The planets that survived the initial expansion find themselves in a new, unstable environment where the rules of the last 4 billion years no longer apply. The distance that once provided the perfect balance for liquid water and biological life is now the front line of a stellar invasion. This growth is not a sudden event, but it is relentless. Every kilometer the sun gains is a kilometer of the void that is erased. The scale of this expansion is so vast that it renders our human concepts of distance irrelevant. We measure our lives in meters and kilometers, but the death of the sun is measured in astronomical units, in the swallowing of planetary orbits, and in the conversion of a void into a furnace. The beach ball of fire has arrived, and the inner solar system is now a memory written in plasma. The sheer scale of this event is not a guess, nor is it a poetic imagining. It is a mathematical certainty derived from the study of the stellar evolution. By calculating the mass of the sun and the rate of its nuclear fusion, we can predict exactly when the shell burning will trigger this expansion. We know the ratio because we have seen it happening elsewhere in the Milky Way. We have looked through our telescopes and seen stars that have already reached this stage. Stars that have become the very beach balls of fire we now imagine for our own home. These distant observations provide the blueprint for our future. We see the red giants in the night sky glowing with a dim ruby light, and we recognize them as mirrors. They are the ghosts of stars that were once like ours, showing us the inevitable conclusion of a low-mass stellar life cycle. The patterns of their expansion, the way they shed their outer layers, and the way they interact with their remaining planets are the data points that allow us to map our own end. This trajectory was first mapped by observing the ghosts of other stars. The blueprint for our own future is written in the light of stars that have already vanished. For decades, the final stages of a star's life were theoretical curves on a graph, a series of equations predicting how a low-mass star would eventually exhale its outer layers into the void, but the theory became a visual reality when the Hubble Space Telescope began to peer into the deepest corners of the galactic disk. Using the wide-field camera, astronomers were able to map the precise geometry of planetary nebulae, those glowing iridescent shells of ionized gas that mark the graveyard of stars. These images revealed that the death of a star like our sun is not a chaotic collapse, but a structured, almost artistic shedding of skin. The images captured the death shrouds of low-mass stars in stunning detail, showing concentric rings of gas and complex bipolar symmetries that look like cosmic butterflies or iridescent bubbles. These are not just beautiful images, they are forensics. By studying the composition and expansion velocity of these shells, astronomers identified a mirror of our own destiny. They found that when a star of one solar mass reaches the end of its cycle, it does not simply disappear. Instead, it pulses. It breathes out its atmosphere in a series of rhythmic waves, creating a layered cocoon of oxygen, nitrogen, and carbon that expands outward at tens of kilometers per second. This is the precise mechanism the Sun will employ. The observations show us that the transition from a red giant to a white dwarf is a process of gradual unveiling. The star pushes its outer envelope away, layer by layer, like an onion being peeled by the pressure of its own internal radiation. Though each ring represents a different epoch of the star's final breaths, a physical record of the stellar wind that stripped the star of its bulk. When we look at these nebulae, we are seeing the Sun's future autobiography, written in glowing plasma across the vacuum of space. The scale of this shedding is immense. A planetary nebula can span several light years across, a vast continent of glowing gas that eventually fades into the background radiation of the galaxy. In the center of these shells remains a tiny white-hot core, the concentrated remains of the star's heart. This core is the final state of the Sun, a dense crystalline ember that no longer fuses atoms, but simply remembers the heat of its former life. The geometry revealed in these images confirms that the Sun will not go quietly, but it will not go violently either. It will drift into this translucent state, leaving behind a ghost of itself that will illuminate the surrounding gas for a few thousand years before the lights go out forever. The precision of this data allows us to see the exact moment the stellar wind overcomes gravity. It's a delicate tipping point where the radiation pressure from the core becomes stronger than the pull of the star's own mass. At that moment, the boundary between the star and the void vanishes. The photosphere, that bubbling ocean of orange plasma we imagined, simply detaches. It floats away, expanding into the cold dark, leaving the core exposed and naked. This is the final act of the star, a slow-motion dispersal of matter that returns the elements forged in the stellar furnace back into the interstellar medium, providing the raw materials for future generations of stars and planets. We see this pattern repeated across the Milky Way, 1,000 different versions of the same ending. Each planetary nebula is a confirmation of the mathematical models, a visual proof that low-mass stars follow a singular, inevitable path. These observations have transformed these objects from distant curiosities into a mirror. We are no longer guessing what happens when the hydrogen runs out. We are looking at the photographs of the event. We see the symmetry of the gas, the temperature of the remaining core, and the rate at which the shell expands. We are watching the countdown of our own solar system reflected in the death of a stranger, but the focus on the star's final breath often obscures a more immediate tragedy. While the nebula is a slow, graceful exit for the Sun, the environment around it becomes a wasteland long before the first shell of gas is ejected. The transition to a red giant is a slow-motion invasion of the planetary orbits, and the biological clock of the Earth is far more fragile than the nuclear clock of the star. The cosmic architecture that allowed life to emerge is not a permanent sanctuary, but a temporary window of stability. The star's expansion is the final curtain, but the air and water of our world will be gone long before the curtain even begins to move. But the end of the planet happens long before the end of the star. the biological clock of our world, is far more fragile than the nuclear clock of the star. We often think of the end of the Earth as a sudden event, a moment where the sun finally reaches out and touches the atmosphere in a flash of heat. But the physics of stellar evolution suggests a much slower, more oppressive erasure. The tragedy of Earth is not that it will be swallowed, but that it will be sterilized long before the sun ever becomes a giant. The models of stellar evolution map this invisible countdown with precision, revealing a relentless upward trend in the sun's output. The sun is not a constant lamp, it is a growing furnace. Its luminosity increases by approximately 1% every 100 million years. High to a human observer, 1% is an imperceptible flicker. Over the course of 1 billion years, however, this incremental growth becomes a planetary death sentence. Here is where the chemistry of our atmosphere turns against us. As the sun grows brighter, the Earth absorbs more energy, raising the temperature of the surface and the oceans. This leads to an increase in the evaporation of water. Water vapor is a potent greenhouse gas, far more effective at trapping heat than carbon dioxide. As more water evaporates, the atmosphere traps more heat, which in turn evaporates more water. This is the runaway greenhouse effect, a feedback loop that transforms the Earth into a pressure cooker. The models indicate that this threshold will be crossed far sooner than the sun reaches its red giant peak. Within 1 billion years, the oceans will not simply recede, they will boil. The surface of the world will become a shimmering white wasteland of salt and steam. The water that once carved canyons and fostered the first cells of life will be pushed upward into the stratosphere. Once the water reaches the upper atmosphere, the ultraviolet radiation from the brightening sun will break the water molecules apart into hydrogen and oxygen. The light, buoyant hydrogen will leak away into the vacuum of space, escaping the planet's gravity forever. We are witnessing the slow hemorrhage of a world. The Earth will not go out with a bang, but through a gradual leak of its most precious resource. The blue marble will fade into a bleached, arid sphere, a silent rock orbiting a star that is becoming too hungry for its own good. The forests will vanish first as the temperature climbs beyond the limit of photosynthesis. Then, the grasslands will wither into dust. Finally, the last microbial colonies in the deep ocean vents will succumb as the seas evaporate into a thick, suffocating haze of steam. The scale of this loss is absolute. Every drop of water that ever fell as rain, every river that ever flowed, and every ocean that ever held the secret of life will be stripped away and cast into the void. The planet becomes a ghost of itself, a desiccated husk of iron and silicate, spinning in a gold-tinted light that provides heat but no life. The distance between the Earth and the Sun remains largely the same during this phase, but the quality of the light has changed. The warmth that once nurtured the dawn now serves as a solvent, dissolving the biological history of a world. This is the reality of the solar timeline. The red giant phase is the final curtain, but the runaway greenhouse effect is the slow dimming of the lights. The Earth will be a dead world long before the sun's photosphere expands to meet it. The silence that falls over the planet is not the silence of a sudden impact or a volcanic cataclysm, but the silence of an inevitable thermal equilibrium. The universe is simply balancing its books, moving energy from the core of a star to the surface of a planet until the planet can no longer hold on to its own essence. This process is not unique to our corner of the void. When When we look at the night sky, it is easy to assume that all stars share a similar destiny, a collective descent into darkness. But the cosmos does not operate on a single script. The way a star dies is dictated by one single immutable factor, its birth weight. Mass is the master of the stellar life cycle, and the difference between a quiet retirement and a violent erasure is a threshold of matter that our sun simply never reached. To understand the gentleness of our sun's end, we must look toward the constellation Orion, at the shoulder of the giant Betelgeuse. Betelgeuse is a monster of a star, possessing a mass many times that of our own. For a star of that magnitude, the end is not a fade, but a scream. When Betelgeuse exhausts its nuclear fuel, the iron core will collapse under its own weight in a fraction of a second, triggering a Type II supernova. It will be a blast so energetic that it will briefly outshine its entire galaxy, incinerating every planet in its vicinity and seeding the surrounding void with heavy elements forged in the heat of the explosion. It is a death of absolute noise and blinding light. Our sun, however, lives on the other side of the mass threshold. According to the established models of the stellar evolution, stars with less than approximately 8 times the mass of our sun are physically incapable of becoming supernova. They lack the gravitational pressure required to fuse elements all the way to iron. They cannot collapse with enough force to trigger a shockwave that blows the star apart. Expectation, a cosmic explosion that resets the neighborhood. Reality, a slow, rhythmic exhale, while Betelgeuse will go out in a flash of gamma rays and neutrinos. Our sun will follow a path of quiet surrender. As it enters its final stages, it will not explode. It will simply let go. The outer layers of the star, no longer held tightly by the core's gravity, will begin to drift away. This is not a sudden rupture, but a shedding of skin. The sun will puff out its atmosphere in great slow-motion bubbles of plasma, casting its outer shell into the vacuum of space. This process is a graceful dissolution. The star becomes a ghost of itself, radiating its mass outward in concentric rings of glowing gas. If we could stand far enough back, we would see the sun, not as a shrinking point of light, but as an expanding sphere of iridescent color, a planetary nebula that slowly thins and fades into the background radiation of the Milky Way. It is the difference between a glass shattering and a cloud dispersing in the wind. The physics of this separation are governed by the loss of hydrostatic equilibrium. For billions of years, the sun maintained a perfect balance between the inward pull of gravity and the outward pressure of nuclear fusion. But as the hydrogen runs dry and the helium burns, that balance tilts. The star becomes unstable, pulsating like a dying heart. Each pulse pushes a bit more of the stellar envelope into the void. This slow shedding is the universe's way of recycling. The oxygen, carbon, and nitrogen that once lived inside the sun will be scattered across light years of space, drifting through the interstellar medium. This gas will eventually settle into cold molecular clouds, perhaps providing the raw materials for a new generation of stars and planets millions of years from now. And our sun will not destroy its surroundings, it will nourish them. The scale of this transition is measured in eons, not seconds. While a supernova happens in the blink of an eye, the sun's transition from a red giant to its final state will take hundreds of thousands of years. It is a patient process. The star simply grows tired of holding onto its outer layers, allowing them to float away until only the most dense, stubborn part of the core remains. And there is a profound stillness in this realization. The terror of the supernova is a fiction when applied to our home. We are orbiting a star that is destined for a peaceful exit. There will be no shock wave to tear through the solar system, no blast of radiation to erase the remnants of the planets. There is only the slow cooling of a hearth, the gradual dimming of a lamp that has burned for 10 billion years. The sun will not fight its end. It will not struggle against the gravity that created it. Instead, it will simply transition from a source of blinding heat to a source of soft, lingering light. The violent deaths we see in the telescope, the great explosions that mark the end of the most massive stars, are the exceptions. The rule for the majority of the universe, and for our own star, is this quiet evaporation. We are part of a low-mass lineage. We belong to the stars that fade. This means that the end of our solar system is not a catastrophe of fire, but a masterpiece of subtraction. The sun will subtract its heat, then its light, and finally its very substance, leaving behind a void where a star once stood. But the disappearance of the outer layers is not the end of the story. The core does not simply vanish. It remains compressed by the weight of everything that once was, becoming something entirely new. It is a transformation of state, a shift from a ball of plasma to a crystalline ember. This transition leaves behind a haunting legacy. The universe files each event in space-time with a meticulous, cold precision, and the sun will eventually leave behind a ghost of its former self. After the outer layers have drifted away into the void, what remains is not a void, but a white dwarf. This is the final concentrated essence of our star, a sphere roughly the size of the Earth, but possessing a mass that defies human intuition. To stand on the surface of such an object, if that were possible, would be to experience a gravity so crushing that a single teaspoon of its material would weigh as much as an entire mountain on our current world. This is not a ball of gas, nor is it a burning fire. It is a degenerate object. In the language of astrophysics, degeneracy refers to a state where matter is packed so tightly that the laws of classical physics no longer apply. The electrons are crushed together until they reach a limit, a quantum wall known as the Chandrasekhar limit, which prevents the star from collapsing any further. The sun's core, once a churning engine of nuclear fusion, becomes a solid crystalline ember. As the physics of low-mass stellar evolution details, the death of a star like ours leads to a specific chemical destiny. The core of our sun will not be made of iron or gold, but of carbon and oxygen. For millions of years, this core will glow with a fierce white-blue intensity, leaking the leftover heat of its previous life into the emptiness of the solar system. But as the eons pass, the heat begins to dissipate. The white dwarf does not have a fuel source to keep itself warm. It is simply a battery that is slowly running out of power. As the temperature drops, a strange and beautiful transformation occurs within the heart of the star. The carbon and oxygen ions, once moving in a hot, chaotic plasma, begin to slow down. They start to arrange themselves into a rigid, geometric lattice. The core of the sun will literally crystallize. It will transform from a liquid-like state into a giant celestial diamond. This is the transition of the solar core into a degenerate carbon-oxygen crystal, a process that turns the remains of our home star into the largest gemstone in the galaxy. This diamond star will not vanish. It will persist. The Gaia White Dwarf catalog from the European Space Agency has mapped thousands of these objects, showing us that They are the most common end state for stars in the Milky Way. They are the silent archivists of the cosmos, cooling over time scales that make the current age of the universe seem like a brief flicker. A white dwarf takes trillions of years to fade. It is a slow, inevitable descent into total darkness. The scale of this time is the true weight of the sun's death. Long after the last remnants of the Earth have been swept away or frozen, and long after the Milky Way has merged with Andromeda to form a new, sprawling galaxy, the crystallized core of our sun will still be there. It will be a black dwarf, a cold, dark sphere of diamond and oxygen, invisible against the blackness of space. It will be a frozen monument to a system that once hosted life, a quiet pearl in a universe that is gradually running out of light. We often think of the end of the world as a moment of noise and chaos, but the reality of the white dwarf is one of absolute silence. There is no wind on a crystallized core. There is no sound. There is only the slow, rhythmic cooling of a dead heart. The sun, which once dictated the seasons, the tides, and the very breath of every living thing on Earth, ends its journey as a cold, hard stone. The universe does not waste energy. Every atom that once formed the clouds of gas in the early solar nebula is accounted for. Some were breathed out into the planetary nebula to seed future generations of stars, and the rest were locked away in this dense crystalline prison. The sun's legacy is not the light it gave, but the structure it left behind. It is a shift from the fluid to the fixed, from the radiant to the reflective. This crystalline state is the ultimate expression of stability. While the red giant phase was a time of bloating and instability, the white dwarf is a state of equilibrium. It is the most honest version of a star, stripped of its ego, stripped of its atmosphere, reduced to its most fundamental stubborn essence. It is a point of infinite density and absolute stillness, orbiting the center of a galaxy that is itself drifting toward a cold horizon. As we look at the current sun, we see a yellow sphere of plasma, a chaotic mess of magnetic loops and solar flares. But hidden deep within that fire is the seed of the diamond. The carbon is already there, built up through the fusion of helium. The crystal is already waiting, latent in the physics of the core, waiting for the heat to fade enough for the lattice to lock into place. We are living in the era of the flame, but we are orbiting a future of ice and crystal. The transition is so slow that it feels like a permanent state. For 1 trillion years, the white dwarf will be a beacon of fading warmth. Then it will pass the threshold where it can no longer emit visible light. It will become a shadow, a ghost. For a piece of cosmic jewelry lost in the dark. The solar system will have become a graveyard of frozen rocks, all orbiting a dark diamond that no longer remembers how to burn. This is the deep architecture of the cosmos. Every star follows a script written in the laws of thermodynamics. The sun is not an exception. It is a perfect example of the rule. It will grow, it will shed, and it will crystallize. It is a process of refinement, where the chaos of a star is distilled into the order of a crystal. The violent energy of fusion is replaced by the eternal stillness of degenerate matter. The universe continues to file these events away, one star at a time. The Milky Way is filling up with these cold diamond remnants, a hidden population of dead suns that outnumber the living stars. We are moving toward a future where the night sky is no longer filled with points of light, but with points of cold, heavy matter, each one the tomb of a solar system. And yet, one final piece of the puzzle remains hidden. And yet, there is a variable in this cosmic equation that remains stubbornly elusive. We can map the birth of a star and predict the cooling of its corpse, but the moment of transition, the actual act of letting go, is where our calculations blur. The specific mystery lies in the asymptotic giant branch phase. This is the final, frantic chapter of a star's life as a giant, where the core is a pulsing engine of helium and carbon, and the outer envelope is a bloated, unstable cloud of gas. In this phase, the sun will not simply sit still. It will breathe. It will pulsate with a slow, rhythmic heave, pushing its outer layers further and further away from the center. But the question that haunts modern astrophysics is exactly how much mass the sun will lose during these final breaths. For years, the consensus was based on general approximations, but the physics of mass loss rates in the asymptotic giant branch is notoriously difficult to pin down. If the sun sheds its mass too quickly, the resulting white dwarf will be smaller and cooler. If it clings to its layers longer, the outcome shifts. We are talking about a margin of error that, on a human scale, would be negligible, but on a stellar scale represents millions of billions of tons of plasma drifting into the void. And as the sun sheds that mass, its gravitational grip loosens, letting the surviving planets drift outward into wider orbits, though for the Earth this slow migration comes far too late to outrun the heat. To solve this, we have turned our gaze toward the ghosts of stars that have already passed this threshold. The James Webb Space Telescope is currently probing this very mystery by looking into the heart of the Ring Nebula. By analyzing the chemical composition and the geometric expansion of the gas shells in the Ring Nebula, the JWST is providing the first high-resolution data on how a star actually exhales its atmosphere. These observations show that this mass loss is not a smooth spherical bubble. It is chaotic, it is asymmetric. The gas is expelled in jagged surges and complex ripples, suggesting that the death of a star is less like a fading candle and more like a slow-motion shattering of a glass sphere. When the sun reaches this stage, it will not just grow, it will leak. The solar wind, which today is a gentle stream of particles, will become a torrential gale. The sun will begin to strip itself bare, casting off its outer skin in great shimmering sheets of ionized gas. These sheets will expand outward, creating a planetary nebula, a glowing shroud of neon greens, deep reds, and haunting violets that will drift for thousands of years across the solar system. This process is the ultimate surrender. The star is giving up its volume to save its core. It is shedding the burden of its outer layers so that the dense, degenerate heart can finally settle into its permanent state. If we could stand on a distant, frozen moon of Jupiter or Saturn during this time, we would see the sun not as a disk, but as a translucent, glowing veil. The sky would be filled with the remnants of our own star, a cloud of recycled stardust that will eventually seed the next generation of planets, and perhaps in some distant eon the building blocks of new life. The uncertainty of the mass loss rate is the last veil between us and a complete understanding of the sun's end. We are watching the Ring Nebula to see our own future reflected in the light of a dead stranger. We are learning that the transition from a giant to a dwarf is not a sudden snap, but a long trembling exhale. As the layers drift away, the turbulence subsides. The violent pulsations of the asymptotic giant branch phase eventually cease. The glowing shell of the nebula expands and thins, becoming a ghostly whisper in the vacuum, until it is so diffused that it vanishes into the background radiation of the galaxy. What remains is the silence, the noise of fusion, the roar of the solar wind, and the heat of the red giant all fade into a singular, cold point of light. The chaos of the stellar death throes is replaced by a profound, unchanging stillness. As the light fades, we find a quiet peace. The solar cycle is not a tragedy, but a closing circle. We have followed the sun from its steady yellow youth through the swelling heat of its red giant phase, and finally to the quiet crystallization of its white dwarf heart. This entire progression is the deepest lullaby the planets have ever known. It is a rhythm of energy and surrender that governs every corner of the observable universe, a slow descent from the roar of fusion into the timelessness of a frozen ember. The finality of this cycle is absolute. When the last of the planetary nebula drifts away, leaving the solar system a dark, cold garden of dead rocks and silent gas, the sun will have completed its primary purpose. It has processed its hydrogen, forged its helium, and eventually exhausted its carbon. It has spent 5 billion years as the beating heart of our world, and in the end it simply lets go. There's a strange comfort in this scale of time. The death of a star is a process so slow that it defies human comprehension. It does not happen in a moment of panic, but in a sequence of trillion-year size. The white dwarf that remains is a remnant of pure density, a small, heavy diamond floating in a sea of nothingness. It will sit there, cooling with an agonizing slowness, long after the Milky Way has merged with Andromeda, long after the stars around it have flickered out, and long after the very concept of light has become a rarity in the deep void. We are the lucky observers of the middle. We exist in the narrow window where the light is just right, where the water is liquid, and where the star is stable. We are living in the golden hour of the solar system. Everything we see, the blue of the sky, the green of the forests, the warmth of the wind, is a temporary gift from a star that is slowly, inevitably moving toward its own silence. As we drift away from the heat of the red giant and the glow of the nebula, we return to the stillness of the present. The sun is still there, a steady yellow disk in our sky, unaware of the ghost it will one day become. The clock is ticking, but the countdown is so vast that it feels like an eternity. We can sleep in the knowledge that the end is a distance we cannot even begin to map. The universe does not rush its endings. It files every event in space-time with a precision that is almost meditative. The solar system will end not with a crash, but with a fade. The planets will either be consumed or cast out into the interstellar dark, orbiting a cooling cinder that remembers the warmth of a billion summers. It is the final breath of a celestial giant, a peaceful exit from the stage of the cosmos. Now the journey comes to a close. The images of expanding plasma and glowing gas recede into the distance. The scale of billions of years shrinks back down to the rhythm of a single breath. The heat of the red giant fades, replaced by the cool, dark embrace of the vacuum. We leave the dying star behind, drifting back toward the quiet safety of the now. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos. Subscribe to Drift with us again